So, welcome to the lecture on multi-degree of freedom systems. So, we discussed in the previous class that when we have a system that has three masses and stiffness elements, and how to write the equation of motions, and finally we can assemble these equations to a matrix forms, and therefore the matrix equation that we derived was, I can write so this is the equation that for a multi-degree of freedom undamped system. So m x double dot plus k x equal to 0. Here m is a mass matrix, and if it is a n degree of freedom system, n degree of freedom multi-degree freedom system, so m is n into n square matrix. Similarly, here k is also n into n matrix, and that is stiffness matrix. Now here we can do this matrix, we can do certain operations. So this is equation number 1. Now we know that inverse matrix. So if we multiply this equation with M inverse, that is the inverse mass matrix. So if we multiply this matrix into this equation, so we will have so here we have now I is the identity matrix. So when we multiply with the inverse of the mass matrix to the mass matrix, it gives an identity matrix. Now here D is the dynamic matrix. So D is equal to M inverse into K, that is dynamic matrix. Now we can, so this is equation number 2. We can think for a solution of this equation as x equal to x sine omega t, where x is this vector, the displacement vector, and capital X is the amplitude of the displacement. So amplitude vector of the displacement, and omega is the frequency. So now we will have x double dot equal to minus, so we will differentiate t, so minus omega square into here this x vector and then sine omega into t. Now we define one term, this lambda, that is equal to omega square, and this is called eigen value, and therefore under root of lambda will give the natural frequencies. So we can write x double dot equal to minus lambda into x sine omega t, and that is equal to minus lambda x. So now if we put these terms into this equation, so we will have here minus lambda I into x plus d x equal to 0. So here we can write, so this will be d minus lambda I equal to 0, and we can put x equal to x sine omega t. So we can have d minus lambda I into x equal to 0. So we have these equations. So this is eigenvalue and this x is eigenvector. Okay. So therefore, if we want to find the eigenvalues, we have to do this determinant equal to 0. So therefore, we have to make d minus lambda I mod equal to 0. This will give the eigenvalues, because all these lambdas is eigenvalue, and corresponding to each lambda, if we put here, we will get this x corresponding to the lambda, and that will be the eigenvector. So now we will take one example and we will try to apply what we discussed. So we have this 3 degree of freedom system that is comprising 3 masses and 3 stiffness elements. So these 3 masses that are 4m, 2m and m, and the stiffness are 3k, k and k. Now we want to know the eigenvalues and eigenvectors of this system. So as we find that we have to first find the eigenvalues, and for eigenvalues we have d minus lambda I equal to 0, this modulus. So we have to find the D matrix. So this D matrix is M inverse into K matrix. So what is the M matrix, M and K matrix? So M matrix, as we have already derived in the previous lecture, we wrote equations of motion and we finally assembled into a matrix, so that mass element, they were diagonal. So here the mass matrix will be, we have this 4m 0 0, it is 3 degree of freedom system, so it will be 3 into 3 matrix, as I said, n into n square matrix. Then this diagonal element to m, then m, and this is 0 0, this 0 0. So this is the mass matrix. Now we have to know the stiffness matrix. So K. So if we remember the K matrix that we collected was the term, first term was K1 plus K2. So here is K1 plus K2. So 3K plus K, and then this was minus K2 minus K2. So minus K and minus K. Then here K2 plus K3. So K2 plus K3. So K plus K, and this was 0. And then these terms minus Kn minus Kn. So minus Kn the last one, minus K and minus K, and this is Kn. So that is K. So this is our stiffness matrix. We can simplify. So that is 4K. This is minus K 0, minus K 0, 2K minus K minus K K. So now we have mass matrix, stiffness matrix, the inverse of the mass matrix. So if we find the inverse of this matrix, so M inverse will be, because it is a diagonal element, so it will be simply the inverse 1 by 4M 0 0 0 1 by 2M and 0, and then 0 0 1 by M. So this is our inverse mass matrix. Now we have to find the D matrix. So D matrix equal to M inverse into K. So we will have 1 by 4 M 0 0 0 1 by 2 M 0 0 0 1 by M. So this is M inverse and K matrix. So we have 4K minus K 0 minus K 2K minus K 0 minus K and K. So now we can have this. So we have to multiply this. So if we want to find this element, we have to multiply this first row and first column. So it is 4K by 4M, other terms are 0. So this is K by M, 4K by 4M, so it is K by M. Then this second term, so this term into this column, so minus K by 4M, and this one, this is 0 0 0, so it is 0, but this term is 0 and this multiply with zeros. Now this term we have second row and first column, so 0 and minus K by 2M, so it is 0 minus K by 2M and 0. Then this term, so this term is second row and second column, so second row and second column, so 0 and this is 1 by 2M into 2K, so it is K by M, and then 0. Then here we have this element, so we have 2 3, so this with this multiply, so 0 and then minus K by 2M here, and the last one, so we multiply third row with first column, so it is 0, then here, so it is minus K by M, and then here, so it is K by M. So we have got this D matrix, and we have to now perform this eigenvalue analysis, and we have to now do the determinant of this matrix equal to 0. So, this, if we now want d minus lambda I, so d minus lambda I is equal to, so it simply get here minus lambda to the diagonal terms, because here d is this and lambda I is unity matrix. So lambda I is lambda I is a matrix with lambda 0 0 0 lambda 0 0 0 lambda. So this is lambda I. So if we do d minus lambda I, so these other terms are 0, only the diagonal terms are non-zero. So this lambda will be minus at the diagonal terms. So we will have k by m minus lambda, and here k by m minus lambda, then k by m minus lambda. Rest of the terms will remain as such. So here minus k by 4m and then 0, here minus k by 2m and then 0, minus k by m and minus k by 2m. So this is d minus lambda I. Now we have to do mod of this 0. So we will have d minus lambda I mod 0. So the determinant is 0. So we will have k by m minus lambda and minus k by 4m and 0 and minus k by 2m, k by m minus lambda minus k by 2m, 0 minus k by m and k by m minus lambda. So this mod is equal to 0. So now we have to solve this determinant. So k by m minus lambda, so we k by m minus lambda, we take first element, and then this is k by m minus lambda square minus, so it is k by m minus lambda square minus, so this is k by minus k by 2m minus k by m, so minus minus it is multiplied with plus, so k by k square by 2 m square. So this is k square by 2 m square. Then this one term, so minus k by 4m, so it is k by 4m, and we have this element, so we take this into this, and this is 0, so there will be no this term. So k by m minus lambda into minus k by 2m so now we may have this, we have to solve this. So k by m minus lambda here, and this is equal to 0. So we can take out this k by m minus lambda, and then inside we have k by m minus lambda square. So it is k by m minus lambda square minus k square by 2m square. Now we have taken this out, and this is minus k square by 8m square minus k square by 8 m square, and that is equal to 0. So now we take this term. So this is k square by m square plus lambda square minus 2k by m lambda, and this is 5k square by 8m square. So this is 4 by 8 m square, and this is 1 by 8. So it is 5 by 8 k square by m square, that is equal to 0. So this is lambda square minus 2 k by m lambda, and this is k square by m square. So it is equal to plus, so because it is 8 k square by 8 m square, so 8 minus 5, it is 3 by 8 k square by m square, and that is k by m minus lambda. So that is equal to 0. So finally this the solution of this equation will give us the eigenvalues. So we see that already k by m minus lambda is giving equal to 0, is giving one eigenvalue. So this is lambda equal to k by m. So one eigenvalue we have already obtained. Now we have to solve this equation, quadratic equation, to get other two eigenvalues, because this is a 3 degree of freedom system, and therefore we will have 3 eigenvalues, and therefore if we solve this equation, so lambda equal to minus b, that is 2k by m, plus minus under root b square. So this square means this is 4k square by m square, minus 4 into 1 into c. So c is 3 by 8 k square by m square, and by 2a. So 2 into 1, so it is 2. So now we will have this. So if we have here k by m plus minus, because we have this. Now 4k square by m square we take outside, so it is 2k by m, and 2 will cancel out. So we will have k by m under root, we have 1 minus, so this is 3 by 8, so 1 minus 3 by 8, and this we can write 1 minus 3 by 8 as 5 by 8, 5 by 8. So this we can have equal to 1 plus minus root 5 by 8 k by m, and that is equal to so root 5 by 8 is 0.791. So it is 1 plus minus 0.791 k by m, and so we are getting 0.209 k by m, and second one is 1.791 k by m. So these are the two other eigenvalues that we have got. So finally our eigenvalues, so lambda, we write these eigenvalues in terms of lower to higher values. So the lowest value is here 0.209 k by m. So 0.209 k by m. Then we have k by m, and then we have the last one, 1.791 k by m. So these are the eigenvalues. So we have eigenvalues, and so this is lambda 1, this is lambda 2, this is lambda 3. So as we have obtained these eigenvalues, now our next task is to get the eigenvectors. So to get the eigenvector, we have to use this equation d minus lambda I x equal to 0. So here we have to put lambda, so here we can have lambda I, and this is xi. So we have to put here the, for each lambda we will get one this eigenvector. So it means that corresponding to each eigenvalue we have one eigenvector. So we have this equation. So d minus lambda I, we know here this k by m minus lambda minus k by 4m, 0 minus k by 2m, k by m minus lambda, and minus k by 2m, 0 minus k by m, and k by m minus lambda. So this is my d minus lambda I, and this is, now we have x1, x2, x3, and that is equal to 0. So we have this equation, and now we can write these equations like k by m minus lambda x1 minus k by 4m x2 equal to 0. So we have now from this we can write minus k by 2m x1 minus k by m minus lambda x2 minus k by 2m x3 equal to so now if we solve these equations, so we can have, if we solve these equations, so we can solve this equation. So from here x2 by x1 we get, and that is k by m minus lambda upon k by 4m. Similarly, we put the value of x2 from here and we can get x3 by x1 in terms of function of lambda. So, now if we put one frequency, the natural frequency, we will get the first mode, and if we put the second frequency, we will get the second mode, and so on. We will get x3 by x1. So, now by solving these equations and using the these eigenvalues, we can find the mode shape, that is the eigenvector of the system, and that was the objective of this lecture. So, I thank you for attending this lecture and see you in the next lecture.